qualitative analysis. So we did a few of the questions from these notes in class on Thursday. However, several people were absent, and also we took it a little bit slower and practiced a few questions that are like the first example before we kind of dug into things today. And so as a result, we're going to be finishing this in class, and I won't be here, and so I'm also going to go through the rest of the notes in this video. All right, so what are we going to do? Well, we're going to start, we're going to learn how to write total. I actually bounce back and forth between using the phrase total or complete ionic equations. It's kind of the same thing, complete ionic equations, and net ionic equations to express mixtures of solutions, and also about using a solubility table to make predictions, a solubility table to make predictions and plan to isolate precipitates. All right, and so to do this, we went through a few examples. So the first thing we did is we went through this example, and so I'm just going to read it, and I'm going to highlight key ideas as I go. So we've got a silver nitrate solution. Silver nitrate, I'm going to highlight that. And it's mixed with a sodium carbonate solution. Sodium carbonate solution. I'm going to highlight that as a solution as well. Okay, and they're mixed together. And we're asked a few things. We're asked what's the total ionic equation, also known as the complete ionic equation, the net ionic equation, and give the identity of any precipitates. All right, so to scaffold a question like this, we've broken this into a few steps here. Part one is we're going to draw a diagram of this mixture with ions floating around in the solution. All right, so we might draw a receptacle, a beaker of some sort, and that's going to have some water in it. And I might indicate that it was made from two other smaller solutions. One was a silver nitrate solution, which was poured in. So it's going to have silver ions and nitrate ions. So if I wasn't sure what nitrate was, I would take a second to look on my common ion table and see that nitrate has an identity as NO3. I'm just going to focus that so I make it a little crisper. NO3 with a negative charge here. And so that means there's a little bit of each of those guys in there, and they're going to float inside, and so there's going to be some silver floating around. There's going to be some nitrates floating around. And in addition, you might make this by adding some sodium carbonate. So again, that's going to have some sodium carbonate poured in. It's going to have sodium ions. That's Na plus, and then the carbonate solution. So carbonate is here. It's CO3 2 minus. Again, that's on our common ion table. So we'd have carbonate in there as well. And I notice that carbonate has a charge of -2, which means there must have been 2 sodiums in this solution for every 1 carbonate. And so I'm going to put an extra sodium in here to indicate that there's twice as many sodiums for every 1 carbonate. Now, we're not going to take those ratios too seriously, because here it also seems to represent that there's a 1-to-1 ratio between silver and carbonate. And that's not necessarily true. There's a 1-to-1 ratio from nitrate to silver, for instance, but silver and carbonate, well, we don't know the volumes or the concentrations of either of these solutions. So in actual fact, there could be a lot more sodium in carbonates and very few silvers and nitrates, or vice versa. And that's something we're going to get into more detail later on in this course. So we're not going to worry too much about that right now. We're just writing 2 sodiums here to indicate the ratio. There's in the compound of sodium carbonate. Okay, so there's a little diagram. All right, and then we're going to write dissociations for each compound. So there's two compounds here. There's a silver nitrate solution, silver nitrate compound. So we know silver nitrate is made of silver, Ag, and nitrate, NO3. And we know a dissociation reaction talks about taking individual, solid and breaking it into little ions in here. And so that means some silver nitrate must have been put into a solution at one point before this happened. And it formed these silver ions, which are aqueous in phase, and nitrate ions, which again are aqueous in phase. And that's the first dissociation reaction. And the next is the sodium carbonate solution. And we talked earlier about the ratio of positive charges to negative charges on sodium and carbonate, meaning you had to have two sodiums to balance the charge from a single carbonate. So that means the sodium carbonate has an Na2. This 2 is just like the 2 in H2O, right? It says there's two sodiums for every one carbonate. And that would have been a salt at one point, a solid salt that was broken into two sodium ions and one carbonate ion. All right. So we're going to write the complete ionic equation here. And so that's what happens when these ions mix together, the mixing of these ions together. And we're going to see if there are any precipitates in the product. So the first thing I'm going to write are my reactants. So all these ions floating together here. Now my silver, my nitrate, my sodiums, and my carbonates. And they're going to mix together, and maybe there will form some precipitate, some low solubility product. A precipitate is something that has low solubility, and therefore it doesn't dissolve well when mixed in a solution. So I might look on my solubility chart and see if any of these ion combinations that are in this diagram, any of the pairs of ions might form a low solubility compound. So it looks like there's 4 different possible combinations. So maybe I'll start with nitrate. I'll start with the negatives. I'll start with nitrate and see if maybe it bonds to form a low solubility compound with sodium or with silver. Now, when I say if I'm starting with nitrate, that's a negative anion. So I might look down and say, oh, here's nitrate here. Okay, so when I look at what positive ions it interacts with, it looks like it reacts with all of them in the same way. And the way that it reacts with them, it forms a soluble compound. The solubility of nitrate compounds is soluble no matter what positive ion they're binding with. So that means that sodium nitrate or silver nitrate, neither of them are going to form, pardon me, I was pointing at silver there, neither of the silver nitrate or sodium nitrate are going to form a low solubility precipitate. Okay, so now we'll look at carbonate and say maybe carbonate forms a salt, or pardon me, with sodium, or maybe carbonate forms a precipitate with silver. Now, we added sodiums and carbonates together, so it's already, right? And that's what these guys came from. So it's unlikely that sodium and carbonate are not soluble in water. They're probably very soluble. So let's just double check that. If I look down, I can see, okay, I've got carbonate all the way down here on the bottom in my negative ions. And I might look and say, oh, it reacts with alkali ions to form soluble compounds, also protons and ammonium ions. Well, what's an alkali ion? Well, if I look on our periodic table here, alkali is a bit of a vocabulary. So I might, if you don't know what alkali metals are, you'll take a second to take your pen and look on your periodic table and write that these are the alkali metals. And while we're at it, if you didn't know that all of these metals were alkali metals, which maybe I'll highlight yellow, that means lithium is an alkali metal, and cesium is an alkali metal. And they all are in a group like this because they all have a very similar reactivity pattern. They all react similarly. While we're at it, we'll also talk about these guys, because if you didn't know what the alkali metals are, chances are you also didn't know what this family is called. They're called alkaline, close, alkaline earth metals. All right, and those are these guys up here. And that's just some basic chemistry vocabulary, so great. Alkali metals. So when we're on our solubility chart, wait, so sodium, we were talking about sodium. Sodium is an alkali metal. And so Na plus, sodium with a positive charge, an ionic form of sodium, is an alkali ion. Sodium is an alkali ion. So if we turn back to our solubility table and we say, okay, what's carbonate going to form a bond with, or a compound with? Well, when we look at alkali ions like sodium ions, that's this alkali ion, like sodium, looks like it's going to form a soluble compound, which confirms what we thought about sodium and carbonate based on the fact that when you mix them in water, you're able to get a solution in the first place. Okay, that only leaves carbonate and silver. So I look at carbonate, it looks like it forms only soluble compounds with these substances, which means all the other positive ions you could possibly mix with carbonate are going to have a low solubility. That means silver and carbonate are going to precipitate out of a solution. They're going to drop out. They're going to form a solid. Okay. So that means this guy is going to form a silver, and silver has a positive charge of 1 plus, and carbonate has a 2 minus charge, which means we're going to need 2 silvers to balance the charge from this 1 carbonate. Indicate that with a little 2 here. And that would be solid. It's going to drop out of the solution. And that little arrow indicates that this solid is going to drop out as a precipitate. And we're going to have these leftover ions just floating around. Na plus, aqueous, and nitrate, which is also aqueous. Okay. Now, to move on to the net ionic equation, we're going to rewrite this complete ionic equation, and we're going to remove all these spectator ions, the ions that did not react. We're going to take those out. So that means I can see on the left and the right my sodiums. Oh, I didn't balance that. What a jerk. And that means I needed 2 silvers here, which means I needed a 2 here. Okay. I can remove these sodiums. I can remove these nitrates. And so I'm left with just silvers, my reacting ions. So my silver ion, AQ, and a carbonate ion. And they form a silver carbonate solution, compound that just sinks out, is a solid, and drops out. Now, you don't really need to always write that little arrow there. It's implied with this, the fact that it's a solid. I'm just indicating it here as a little bit of extra indication. So what a net ionic equation does is it demonstrates just the precipitation reaction, the act of two ions coming together and forming a solid. And why is that? Why do we do that? Well, sometimes we only care about the precipitate. And the sodiums and the nitrates we kind of ignore, and that's maybe often true because in a lot of situations there's lots of little inert ions floating around in water that we don't care about. However, a complete ionic equation, that's good because that tells us the whole story. It tells us all the stuff that's in the solution to begin with, and some of those bind together and form silver carbonate solid compounds, and others are unaffected. They still float there. Now, if we're asked for the identity, meaning what is the precipitate, well, that's our silver carbonate, and it's a solid. Okay, so it might help us to recognize that as we mix these together, we're going to get an after picture as well. And that after picture is going to be pretty similar to the before picture, except now we're going to have this precipitate, this silver carbonate, and it's solid. And we'll still have these other spectator ions floating around. We'll still have these sodium ions, and I guess we had two of them, and nitrate ions, and so on. Now, if you want to get technical, it's very unlikely that all of the silvers hooked up with all of the carbonates and fell down here. First of all, it was very unlikely there was a balanced rate of silvers to carbonates in the first place. Very unlikely there was twice as many silvers as there were carbonates. So there's likely some unreacted silver or unreacted carbonate in the solution. And also, there's probably some of both floating around that just never met up to form a solid salt. And we're going to look at some other factors that affect this in the future. However, this diagram is a simplified diagram. And as is this one, it just helps us to get a picture of what's going on. Because sometimes there can be a lot of abstract stuff on a page, a lot of numbers and letters, and we want to take a second to really think, well, what are we really talking about here? And so, hopefully a picture can help us understand that process. Okay, so we'll put a little asterisk next to simplified. Okay, so if you've made it through this question and you feel like you kind of are getting it and you want to see if you really understand it, I would encourage you to go and test yourself by trying question 1. Back here, it's very similar in nature, requires most of the same steps, and it can help you to practice and make sure you're 100% there. So I might encourage you to stop this video and go try that question and check your answer and see if that's something you totally understand or not. All right, let's move on. In the notes. Okay, so we left off discussing this idea that we had a solution and it has either barium ions or magnesium ions in it, and maybe that's all you know. Who knows exactly what the story is behind why you have this barium or magnesium solution and you're not sure which one, but you know that one is poisonous and one isn't. One is like something you can drink and you typically do and is in some of the compounds that are pretty important to your life. And the other one is pretty bad. You want to make sure you're not drinking it. So maybe you want to test water to make sure it isn't the water with the barium in it. So how can you do that? Okay, so again, we've tried to break this into some manageable steps for us. So we want to, okay, I'm going to highlight some key ideas about the question before we move on. So the question either has barium ions or magnesium ions. And we're going to suggest a method by which these solutions can be analyzed to find out which ion is present. And we're going to be specific about any compounds that are added. Okay. So the first question is, can we use our solubility table to find an ion that we could add to our solution that will create a precipitate with only barium ions, or maybe it'll react with only magnesium ions? And that's the question. So we're going to look and see, is there some ion we could add that forms low solubility with either just magnesium or just barium. And I might take a look, and so let's take a look at the bottom. Let's start there. So I can start down here. Do any of these negative ions, when I mix them with barium or magnesium, what would happen? Well, it looks like they would both form low solubility precipitates. So these guys would react the same with magnesium and with barium. So when I see a precipitate form, it doesn't tell me if it was the water with barium in it or not. And that's true for hydroxide as well. Hydroxide, as we saw when we went to Britannia Mine, is an ion you can put into a solution that raises the pH and binds to metals to drop them out of solution, cause them to have low solubility. Okay. So it's going to do the same for magnesium, because magnesium and barium, neither of them are alkali ions, neither of them are alkali metals. So none of those are going to be soluble. Okay, so let's move on. Okay, if you add sulfide, well, it looks like it reacts with magnesium and barium the same way to form a soluble compound, one that doesn't really bind strongly enough to be kept away, to be kept together in the presence of water. However, sulfate binds to the barium preferentially. It's going to bind to barium and form a low solubility compound, but not magnesium. Magnesium will be soluble. So what that says is we can add some sulfate to our solution. And that's going to bind to the barium and make it sink out of the solution. And that won't necessarily happen with the magnesium. In fact, there's no indication to suggest it would. And so sulfate will form barium sulfate, solid, and sink out of the solution if barium is present, but no precipitate if magnesium is present. No precipitate. I could definitely have written that more clearly. All right, so now we can't just grab a handful of sulfate and pour it into a solution, because sulfate is a negatively charged ion, and so you know if you gather too many electrons on a hot day by rubbing your socks against the carpet, say, you get electric shocks, right? So too many negatives are sort of unstable. They're definitely unstable. I mean, so you can't just have a beaker full of sulfates, just a bunch of sulfates hanging out in a beaker somewhere. And so in the chemical stores, there's never going to be just a bunch of sulfate. And that doesn't exist because it's too electronically powerful. It would be explosive in nature because of all those negatives in such a small space. So all those negative charges have to be balanced in a salt with positive charges. We have to look for a compound. It's not sufficient to just say you need sulfate. You can't just go get sulfate because it's dangerous. It's too dangerous to have a meaningful amount in any circumstance. So instead, you need to ask for some salt that contains sulfate and also some other substance. And you need that compound to be soluble in water. Okay, so let's take a look and see if we can figure out what positive ion we could mix with sulfate. Positive ions we're looking for now that will mix with sulfate and form a soluble solution. Okay, so this really suggests we can choose, if we look at sulfate, as if we want something that will dissolve in water, we can really have any other positive ion that isn't one of these. Even magnesium, actually. So we could add magnesium sulfate or whatever. We suggested in class we could add hydrogen ions because they're soluble with all ions, including sulfate. Or ammonium is something somebody suggested. And in addition, you could also use any of the alkali ions, which are actually listed for us up here, in case we didn't notice. All right. In fact, I hadn't noticed that in a while. I usually don't look up at this part of the periodic table because it doesn't hold information, of the common compound solubility table. It usually doesn't hold information I need, so I actually forgot that that's up there. All right, so anyway, we can take our pick. Sodium is nice and cheap. It's not very exotic, not very hard to get. And that's usually true with nitrates as well, so you're going to find a lot of nitrates. Obviously, nitrate won't work with sulfate. It's negatively charged. But if you want common neutral ions that are easy to plan for because they're cheap, nitrate is the common negative one. Sodium is a common positive one. Now, there's nothing saying we can't choose lithium ions to be to have some fun. And lithium, maybe you want that in your water because it's a mood stabilizer. I don't know. All right. So we're going to choose an ionic compound. You know what? Hydrogen ions were suggested. So some possible answers could have been a lithium ion solution or compound. So lithium sulfate, solid, or suggested in class is sulfuric acid. So you're going to be, we learned at Britannia that acid can help to make metals dissolve. So we're going to hope that your barium sulfate solubility isn't negatively affected by all the acid from sulfuric acid. But as far as we're concerned, we're just looking for positive ions that we could throw on there. And the most common one I would say is sodium sulfate. I can say with great confidence that I can find sodium sulfate in the science supply room without actually ever having to look, because I just know that it's going to be so common to have a sodium bound with sulfate. But maybe lithium might be a little bit harder to find. I might be surprised if I saw some lithium sulfate. And so your answer may vary. So choose one that you like. Maybe you want a crazy, exotic, radioactive ion like francium or something. And that's really your choice. Okay. So let's take a look at what would happen with a complete ionic equation and a net ionic equation if the solution contained barium ions. Because remember, we weren't sure, right? But we know that if it did contain barium ions, so I'm going to choose going to choose the protons here because that was what was suggested in class. So I'm going to say, let's see, so I'm going to add some barium ions, those would be aqueous, and some hydrogen ions, or also known as protons, and a sulfate ion. And they're going to bind together, the barium and the sulfate. So this is the complete ionic equation. And I'll maybe highlight that. It's a complete ionic equation. You know what? Maybe I should highlight this with a different color. So yeah, we'll call it pink. And so anyway, we've got some barium sulfate, which is going to be a solid, and we've got some protons just hanging out. And the net ionic equation, which we'll highlight with pink, it's going to be just the reacting ions. Barium plus sulfate, aqueous, when mixing together, is going to form barium sulfate solid. All right. And so we're going to use those to illustrate. So basically, the prediction is that if barium ions are in the solution, well, adding sulfuric acid will cause a barium sulfate precipitate to form. Okay. And let's just go through the other possibility, which is if our solution contained magnesium. So the complete ionic equation is, well, we wouldn't say we have barium, we'd have magnesium plus 2 protons, aqueous, and some sulfate, which are aqueous as well. And when we look, let's just double check that sulfate, well, I think we already chose these two, or sulfate, so it wouldn't bind with either of these, but let's just double check. Sulfate, and we see magnesium is one of the others. It's not one of the listed compounds. Same with protons. It's a different positive ion. And so these guys combine with sulfate in a soluble way. So we would say there's no reaction. And so actually maybe a more formal complete ionic equation just to say that you have magnesium ions and some protons and a sulfate. And then when it comes to the net ionic equation, remember we're only going to be listing the substances that react. Well, nothing reacts. There's no reaction. This is maybe a more appropriate place to write no reaction. So, if magnesium ions are in solution, adding sulfuric acid will not form any precipitate. And that's a way we can test what our solution holds. Maybe it holds some barium, maybe it holds some magnesium. Okay. So, if you want to test if you understand this concept, I would encourage you to move on to question 2 on the back and see if you can find a way to take out each of these substances. However, 2 might be a little hard without following through example 3. So if you want, you can stay with us. We're going to talk about filtration a little bit and how we use that to filter out more complex solutions to sort out individual ions. All right. So, I'm just going to stand up for a second because I can't pause a video and grab a filter. All right. So, once you have a situation like we did in our first example, which is we ended up with precipitate at the bottom of our solution, what we will often want to do is remove that precipitate from the solution. And we saw stuff like this in Britannia mine when they let all of their flocculant and metal hydroxides float to the bottom. And then they wanted to remove them, so they removed them with a filter. They also added air pressure to help speed up the process. However, you don't really need air pressure. You can actually very simply take some filter paper, fold it into a cone, and put it in a funnel, just like this. And we're going to be doing some of this next week. And you can just pour your solution straight into this filter, and it's almost like making coffee. You got a coffee ground and water mixture up here, and out flows a solution that is relatively clear, hopefully. And, I mean, not when you're making coffee. But it keeps all the precipitate, the solid stuff, in the top. And that's like, then you take out your filter, and if it was coffee, you would throw it away. But if it was, well, for sure, if it was your silver carbonate, you might want to take that silver carbonate, unfold your filter paper, let that stuff dry out, and then you've got a powdered silver carbonate. And maybe then you can do some isolation processes to get the silver out of it. All right. So we're going to use that principle to work through a more complex example of a sludge that has 3 different ions in it. Okay. So we have some chemical sludge that has silver ions, strontium ions, and magnesium ions in it. And they're just all floating around in there. There are positive ions and, there are negative ions in there as well. But that's what we're starting with, and we're not really focusing on the negative ions right now. Just like with the magnesium and the barium ion example. Okay, so that's what we're starting with here. And we want to separate these ions for resale. We want to get them apart. We want to separate these ions. So we want to find a way to take all of the strontium out, take all the silver out, take all the magnesium out. And we're going to isolate them one at a time. And we're going to do that using precipitation. Okay, so how are we going to do this? What's the procedure we can do? Well, what we're going to want to do is we're going to want to find something we could add to the solution that's going to take out one of these, but not the others. So we're going to think about an ion we could add that will react with one, but not all 3, and not 2. So out of our silver ion, our magnesium ion, and our strontium ion, can I see an ion that I could add that will bind just to one. And so actually I could see a few different possibilities. The first possibility so maybe I might think, maybe sulfate, because I can see a silver ion in sulfate. I'm going to actually keep this diagram right here next to it. Okay, so I can see a silver ion in sulfate. However, I don't see any magnesium, but I do see a strontium ion as well. So actually, if I added sulfate, it would bind to silver and strontium and take them both out. I want to choose one that's going to only select one of them. And if I look, I'm like, well, okay, it looks like maybe one of these ions is going to be effective in bringing out silver while leaving the magnesium and the strontium in the solution. Okay. So maybe the first thing we'll do is we'll add a compound that has what we call a halogen ion in it. And kind of like sodium from before, chlorine is a nice cheap one, a little less exotic than bromide and iodide. Although these guys are actually pretty cheap too, relatively speaking, because all three are used pretty commonly. Like chlorine is used for pools, and bromine is used in hot tubs, and iodine is used in cleaning wounds. So these are all actually quite common in everyday life. So chlorine is for sure the cheapest, also because I can think of a compound that's really common that contains chloride ions. So the first thing I want to do, step one. We're going to add a chloride ion. But we can't just add chloride ions, we have to add a compound. So what's a compound that's otherwise going to be neutral? So we talked about how like a lot of these guys, these positive ions here, they're all often very neutral. So if you want to get funky and like fancy, you can add some rubidium or something like that. Wait, is that rubidium? Do I even know that one? Or rubidium. It's not very common. However, sodium chloride, well, that's pretty easy to add because that's just table salt, right? So I'm also sort of thinking about what's most common. So I'm going to stick with sodium ions. Here. All right, so I'm going to add sodium chloride, which is salt, and it's a solid. All right, so then I'm going to write a net ionic equation. So first I'm going to write a complete ionic equation. And so that's going to look like I'll have some sodium ions, some chloride ions. So you don't actually have to write the complete ionic equation, but I'm going to write it just so that we're sure what's happening. We're going to have some silver ions, some strontium ions, and some magnesium ions. And that's all going to form. And we talked about how it's going to form a silver chloride solid. But the rest of these guys are spectator ions. They're going to stick around. I'm going to run out of space here. Strontium ion, also aqueous. And, what am I forgetting? My magnesium ion. That's also aqueous. All right, and so our net ionic equation is just going to be our silver ion plus our chloride ions, and that forms silver chloride solid. Okay. So now I'm going to have a solution after step one that has silver chloride at the bottom and solution with some strontium and some magnesium, and also, I guess, that other spectator ion, which was sodium. Drew that kind of small, but I think you get the idea. So now we need to get rid of that silver chloride before we start making other precipitates. And then we have to separate precipitates, and that gets actually a lot harder. So step 2, we're going to filter out the precipitate. So we're going to filter out the AgCl, which is a solid. And that's just a short step. We're going to add that through a filtering system, add the whole solution in here, and we call filtrate, like the coffee in a coffee situation. It's going to filter out into a new beaker. Okay. And the precipitate is going to remain at the top, or the grounds, if you can think about coffee grounds. Okay, and then we would take that to dry it out. All right, so we've got some silver chloride. All right, so now, step 3. Okay, so now what do we have? Now, so I'm going to write out what we have. We know we already have in our reaction, so we've got complete ionic equation. So we haven't even added anything yet, but I know that I have sodium ions, some strontium ions, and magnesium ions. And I want to get rid of, so the sodium is not really going to go anywhere. So actually I'm going to kind of ignore the fact that I've got sodium in there. But I want to get out the strontium and I want to get out the magnesium. Okay, so what compound can I add to either take out only strontium or only magnesium? And so I'm going to look and see if I can find a compound that will take out strontium, but not magnesium. I look and I say, oh, it looks like sulfates will take out strontium, but they won't take out magnesium. Magnesium is going to be left soluble in the solution. So I'm going to add a sulfate compound. And to keep things simple, I'm going to keep adding sodium sulfate. So step 3, I'm going to add sodium sulfate, sodium SA2. So we're going to add some of sodium sulfate. So that means we're going to add 2 new ions. I think I'm going to use some more colors here. So sodium ions, aqueous. Oh, I don't even need to say that I've got sodium. I already had sodium. Plus some sulfate ions. All right. How's that going to react? I'm going to run out of space for sure. But that means the sulfate is going to react with our strontium to form our strontium sulfate solid, which is going to precipitate out. Actually, I'm going to indicate that the silver chloride is going to precipitate out as well. And I'll have all these other spectator ions. I'm going to try to use with another color here. So what else do we have left? We have some magnesium ions. We have some sodium. Oh, and that's it, right? That's not so bad. Okay. And so again, now we're going to need to take out that solid. So step 4, filter out the strontium sulfate solid precipitate. Okay, and so that gets this guy out. And so now we're just left with magnesium and sodium in the solution. So step 5. So we're going to need something that takes out magnesium. So I'm going to write out my complete ionic equation. Oh, I forgot to write a net ionic equation for this precipitate. So our net ionic equation, I'm just going to try to write that in another color here to make it nice and different, because it's a little cramped there. I wish I'd realized that. So that's our strontium ions plus sulfate ions, and those mix together to form blue pen gun. There it is. Strontium sulfate solid. Okay, so our complete ionic equation for this one, so we know we have sodium left in our solution, and we have magnesium left. We can kind of add whatever we want as long as it's going to take out magnesium in a new precipitate. So I need something that takes magnesium, is going to leave that sodium in the solution. And it looks like I've got a few different options. So it looks like maybe hydroxide would work. I could take out my magnesium and would leave my alkali ions like sodium. So maybe I'll add some sodium hydroxide. And again, you don't have to add sodium necessarily. We'll add sodium hydroxide. So maybe I'll make that a new color here. Or maybe I'll keep it sodium hydroxide solid. Okay. And so I'm not going to make a note that we have sodium here still, but we are going to add hydroxide. That's going to be the new substance. And that's going to react, and the magnesium and the hydroxide are going to fall out of solution. So we're going to get a magnesium hydroxide, also known as milk of magnesia solution. It's going to fall out because it's solid. And you're left with sodium in your solution. Okay, and the net ionic equation here is magnesium aqueous plus our hydroxide. That's going to form magnesium hydroxide. That's a solid. Okay. And so the last step, we'll filter out our magnesium hydroxide. I'll use blue again for that. And then we've got 3 different precipitates. And so that is a procedure that is going to separate out each of these ions into a different compound. And we can use some material that we'll learn later in the year that's going to help us to then isolate the metals specifically from our solution. Now, I want to say I noticed as I was working through this, I could see at least one other way to solve one other procedure you could add. Instead of adding salt, table salt, sodium sulfate, and sodium hydroxide, you could add other things. And I don't just mean changing the positive ion to some other neutral ion. I could see some totally different solutions where you could have taken out the magnesium first and the strontium second. So there's a lot of options for these paths, and we're going to try to just get our hands dirty and try and feel out a method that works for us, and it may be different than our neighbors. All right. So with that information out, I'm encouraging you guys to go and tackle all 4 questions from the self-test on the back. All of these should be accessible questions to us. And I'm going to write up a solution video that I'm going to put up on Google Classroom as well. So if you have any questions about any of these, or if you get stuck, I encourage you to check on there. However, because there's so many ways to solve these, I would really encourage you to maybe pair up with somebody and work with them in class. And then you can bounce some ideas off each other. Anyhow, send me any emails over the weekend. Even though I'm away, I should be accessible by email, at least in the evenings. All right, good luck, and have a great weekend.